What about this one? What about when I multiplied A times dj of C? And this is where I want to do a little bit of creative work here, I suppose. Maybe we go on this one. I'm going to kind of level up right now to show you how deep this thing goes. So many mathematicians assume matrix multiplication is trivial. I do not assume that. In fact, I say matrix multiplication is not only non-trivial, it's one of the most powerful operations that we have, and we should spend time studying it. What was dj of C? How did I write that out? It's a dilation matrix. I agree with that. In plus C minus 1 times EJ times EJ transpose. This thing was an m by n. How did I know the size that this matrix should be? It must be n by n because it was supposed to be square, and I'm multiplying on the right. That immediately means what about this size? N by n. This thing over here was how big? N by 1. This thing over here was n by 1. N by 1 transpose, which we call 1 by n. Question, can I bring A over to the other side? Why not? The inner dimensions most agree. And another way to say that is matrix multiplication is non-commutative. It breaks all the rules of what you're used to in R, right? So don't bring R into this. Okay. We are going to learn a theorem today that says that if I take a matrix A and I multiply B plus C, can anybody guess what this theorem is going to say? A times B plus A times C. Can you guess what we call that theorem? Distributivity of matrix multiplication over matrix addition, right? Assuming that these are all conformable, right? If that theorem is true, what am I going to do with this multiplication? A times In plus A times C minus 1 times EJ times EJ transpose. Well, what was A times In? A. Just doesn't, it literally plays the role of the number 1, right? We call 1 in the real numbers the multiplicative identity. This is now called the identity matrix because when you multiply by it, you don't do anything, right? It plays the role of 1. You don't change the columns, you don't change the rows, you just leave it alone, right? Over here, we'll have another theorem that says when I multiply A times C times B, if these things are conformable, can you guess? Yeah, that's C times A times B, and another way to say that is that C times A times B. In other words, scalar multiplication can go through any direction that you'd like, right? So can you guess what we can do with this thing? C minus 1 can come out front, and then I've got A times EJ times EJ transpose. All right, let's do a quick analysis here. This is Mn. This is n by 1. This is 1 by n. Right now, we've associated these ones. We will have a theorem in matrix multiplication that says if I take A times B times C, can you guess what that's going to be equal to? A times B times C, assuming all of those are conformable so that their dimensions agree in the way that they're supposed to, right? Which means that instead of associating these two together, could you guess what we do here? Yeah. So now we've got something that looks like this. We've got the entire matrix A. We've got a C minus 1. And then this is now A times EJ multiplied by EJ transpose. Anybody know what this is? And I'll give you a hint. Okay, one way to think about that is the linear combinations of the columns of A with scalar coefficients defined by the entries of EJ. What are the scalar coefficients of this thing? They're all zeros. So basically you cancel out almost every single column except which one? The jth column. So what is that thing right there? Yeah, it is the jth column of the matrix A, right? Okay. So now this thing is now A plus C minus 1 times the jth column of my original matrix, and then I'm going to place that column in a very special place. So let's go ahead and look at this thing. How big is the jth column of my original matrix? M by 1. How big is this thing? 1 by n. How big is this? M by n. What is that matrix? Okay, so I agree with you that the thing on the left-hand side is a column vector. The thing on the right-hand side is a row vector. What does that immediately mean about the operation in between the two of them? Ooh, you've been suffering. I mean, most people say, oh my God, you're so smart. But what that means is you've been feeling pain in the privacy of your own space, right? Just like a good athlete feels pain when they're training, so too a good mental athlete or mathlete feels a lot of pain and then like, oh yeah, I know this, right? So that's an outer product because the thing on the left is a column vector, the thing on the right is a row vector. Which outer product is it? So if I were to actually write that thing as a matrix, how big would the matrix be? Yeah, by dimension analysis, this thing must be an m by n. What's the first entry? If assume j is not 1. What's the first entry of this thing? 0. So how do I form the outer product? I take this entire column vector, and in column 1, I multiply by the scalar 0. So now I've got a 0 vector, right? That's column 1. And then I go all the way down to the j minus nth entry. What's the j minus nth first entry of this thing? J minus 1? 0. So this thing right here is going to be column j minus 1. What's in column j? The jth column of? Other people hear those sounds too, right? That's not just in my head. Okay. Just got to check every once in a while, you know? Okay, so now you've got these columns. What's the j plus first column of this matrix? 0, all the way down to the last column, which is also 0. We will have a theorem in matrix scalar. We actually already covered this one, right? If I have alpha plus beta, and I multiply by the matrix A, that's equivalent of saying alpha times A. I guess we should call it B in this case so that we're not... Sorry, am I talking too fast? Yeah, so in this case, what does this do? What is, you know, one thing that I would ask you is, where does this particular, perhaps we call it addition, take place? What type of addition is this? Scalar addition. So would you agree that in that space I can actually flip these around with no cost? My hand is a suboptimal eraser. Okay, so let's go ahead and distribute this. What does this particular addition do to that matrix? Yeah, so now I've got whole idea here. Got the jth column all the way down to the nth column minus. Now I'm going to take away from that this thing, right? 0. Here I have the jth column. That's 1 times that thing, right? All the way down to 0. And what am I going to add in its stead? C times that same matrix. 0, the jth column, 0. So let's see what happens. I take the original matrix. For everything but the jth column, what do I do to it? Not a damn thing, right? I don't do anything because all of these are zeros. So everything but the jth column isn't even touched by this operation, right? In the jth column, with the -1, what do? I subtract the original jth column that I started with, and then I replace it by C times the jth column. Right? So now the matrix that I get out is going to be something like 1 C times the original jth column, and that's going to be in the jth position. So this is going to be what we call the jth column. And then all the way down to the last column of my original matrix, which was an. So what, in words, what did it mean when I multiplied algebraically, when I multiplied a on the right-hand side by d sub j of c? Jth column, because I'm multiplying on the right. But you know what he was doing, right? Jump to conclusions. What was the conclusion that you jumped to? If I don't multiply j on the right by djc, but instead I multiply j on the left by djc, what would I do? I'd scale the jth row by the scalar c. So this was very, very general, right? How often did I write down dimensions? All over the place, right? You could say that like the voices in my head just won't leave me alone, right? Because I'm like literally thinking about dimensions the entire time I'm doing this, right? So what did this operation do when I took A and I multiplied on the A by djc, by the dilation matrix whose jth n3 was equal to c and everything else was 1? Scale the jth column of A by scalar c. If I don't write what I do to the rest of the columns, what's the claim? Don't do anything, right? And you would know that because the other main diagonal entries of this thing are all 1. And leave all other columns the same.